Hello guys, welcome to a new class. The motivating video for this class will now be this.
You like probability theory. You like probability theory. You like probability theory. Probability theory.
So you like probability theory. Now let's go back to talking about, yes, you better. Let's now go and review what we did for, I hope so, guys, right? It's much better than programming, at least for me. I was trying to build something and I'm a god-awful programmer. I'm so proud of myself. I made an algorithm that probably any one of you could have succeeded in making in 5 minutes, but it took me 2 days, right? And it works tremendously slowly, but it is able to do what I wanted to do. Maybe if you're interested, I'll show you. That video, no, I made it at another night at 5 a.m. Okay, guys, so let's talk about the beta distribution. So once again, let's just go through the ideas to be sure that you really understand this distribution. It's pretty interesting, at least especially in today's time. So as I mentioned, maybe you will help me recall, this is the definition of the density function for the beta distribution, where you notice that x is between 0 and 1. Would anybody like to comment either by text or verbally to say, maybe very roughly, what's the idea of this scary looking formula? What is it in general that we think we can try to do with it?
You can take value you can take values of alpha and beta and approximate this distribution to really any shape to fit your data.
Right, very good. I'm not sure about, I cannot tell you for sure if it's any shape or not, but definitely many shapes, right? So you can kind of adjust this A and this B and make it look like all sorts of various shapes. And that's one thing about it, but the more important thing we will again talk about today, right? It's just the beta distribution is a sort of inference. Is that what you're trying to do with it? Is you're trying to estimate the probability of an unknown event. By the way, right there, what you said was absolutely very beautiful. But just to mention again, we would like to figure out how evidence updates our idea about the true probability. Yes? So there is, I mean, let's say I toss a coin or I perform some experiment, or there is some probability that someone among us is sick with the flu or something, right? So how do you know what's the probability of infection? How do you know what's the saturation within a population? How do you know if a medication is working? How do you estimate such things? But so beta can be very useful for that. And that's why I would like to, again, go over the argument once more. So first, you can see that over the interval from 0 to 1, you can make many shapes. Here is when A is bigger than 1 and B is bigger than 1. Here is where both A and B are less than 1. You have this U-shaped distribution. You can make A less than B, let's say something like that. That's about, if A is equal to B, we have symmetry around 1/2, and so on and so forth, right? You can have all sorts of shapes with this distribution. We can see that. Now, this beta of AB, there is nothing special to it. It's just a corrective factor. You see, it's if we integrate from 0 to 1, just this expression, much easier to remember this expression. Yes, we will get some number, and this number is a function of both A and B, correct? So we divide by that number so that we get the integral equal to 1. That's called normalizing it. Yes, that's what we did for the normal distribution. Why do we divide the standard normal by 1 over root 2 pi? That's because the integral of e to the minus x squared from minus infinity to infinity happens to be root of 2 pi, and we normalize. Yes, Chiara is moved to tear by that, right? By normalization. It is touching indeed. I also get very emotional when I think about it. So there's one instance where doing this normalization is not very difficult. And that's where a and b are positive integers, as in, let's say, a is in this case, well, in this case, we have k and n minus k. I mean, really a is, you see, it's really a should be k plus 1 then, because you see we have subtraction here, right? I do not know why they decided to make it a minus 1 b minus 1. That's the convention, at least that I was exposed to, but that's a bit weird to me. I tend to not remember. But a in this case is what? A is k plus 1, and what is b? B is n minus k plus 1, because you see you subtract 1 here, right? That's just a trivial thing. I get confused with it very frequently, but it's, I think at the moment, I imagine it's trivial. So we know that this integral here is equal to 1 over n plus 1. And we can do that, we can know that by just using combinatorics. Obviously, you can integrate. You can use a computer, or you can try doing integration by parts, or some other way of dealing with this problem, and you can figure it's 1 over n plus 1. But the beauty of combinatorics is sometimes you can figure out the answer without doing any complicated calculations. So how do we do that? So we come up with a story. So the story we came up with was this. So we are going to try to figure out what's the probability that we have basically n plus 1 points, atoms, or whatever you like calling them, and they are going to be randomly placed on the interval from 0 to 1. One of the atoms is colored red, the others are black. And we want to know what's the probability that there are k black atoms before the red atom, right? So in this region. So how can we solve that? Well, we can figure out what's, for instance, what's the probability that x is equal to k. X is the number of black balls below the red one in this region, right? We can figure out what's the probability that x equals to k if we know where the red ball is located, or the red point is located. Yes. So given that the red is at position p, we know it's now a binomial, right? It's each of them is equally likely to be anywhere. So probability that any given black ball is here is p, and the probability the black ball is here is 1 minus p. So n choose k, which of the k are to the left of p, and the rest are to the right. And that way we have p to the k, 1 minus p, and minus k. You all understand this formula, correct, guys? You understand how given p, I know how to derive this. It's just a binomial. Good. Now, it's a binomial conditionally that I know where the red ball is located. Otherwise, it's not a binomial. Yes? Makes sense, guys? If I know where p is, if I know that the red ball is in this position, I can ask what's the probability that I have k black balls before it, and then that's binomial, because now we have this. We're assuming uniform distribution, right? So each black ball is equally likely to be anywhere. So for any black ball, we basically, the probability is in this, that it is in this interval is p to the just p, and for k of them it's p to the k times n choose k times 1 minus p to the n minus k. So that's our density function. Good. So what can we do with it? We want to know what is the probability that x is equal to k without this condition. And then we just use the Bayesian property, right? So what is that? I can imagine dividing this interval into many tiny segments. In general, I imagine that it's divided so that I don't have to write it. So it's divided into intervals of length dp, right? And so then I can write a summation like this. So it's the summation probability x equal to k given red at P, probability red is P, right? And the probability that red is P, in our case, is dP approximately. Make sense? Because we're assuming if it's at P, it's P up to P plus dP, right? So it's this region. We're making it a discrete random variable, so to speak. You understand how I get the probability that R is equal to P, it's dP? It's only by approximation. The actual probability is 0, right? So here I imagine it's approximation, and here I add up over all possible P. So I imagine there is this P, there is this P, there is this P. There are only finitely many P's. But if I break the intervals into, let's say, million segments, that would be a very good approximation to the continuous situation. I did not lose any of you yet? Good. Camille, I lost you, you mean, or I did not lose you? Okay. Okay, good. So this is what we have. You understand how we get the integral, right? In general, it's FPdP, where F is the density function at P times the width. So it's like the height times the width. That's the FPdP now represents the probability of getting P, essentially, right? So it's P, or a number that is essentially indistinguishable from P. So in other words, I always like to view even continuous random variables as discrete, but ones where you have incremental changes, barely visible incremental changes, and you have many, many possibilities, right? So it's like you take something and you have pixels, right? And the pixels are very close together. That's pretty much whatever happens with when we watch screen or when we draw a smooth looking curve. It's really made of non-smooth segments. Same thing here. And so we have, this is the summation, right? Summation and choose K, P to the K, just the summation. We sum up over all the binomials. You see, we have for each particular instance of P, we have a particular binomial, and we add up over all the binomials, so to speak, right? So, and that's the integral that we get. We get that the probability that exactly K black points are below the red point is this integral, without knowing where red is located. Right? And this integral, we can then evaluate if we can come up with a different procedure to solve this problem, right? And the different procedure is very simple. Now, what happens, guys? So the only way there are K black balls before the red one is if among them, if you basically have all the possible orderings are equally likely. Right, so the K plus 1 position must be occupied by the red atom, correct? The K plus 1 position is occupied by the red atom. That's the only way this can happen. That's another way of doing it. See, I wrote here as a sequence. You can either think of it as two sequences. So that is telling you that all the n plus 1 factorial orderings are equally likely. You agree? So that's one way to think of it. So every n plus 1 factorial orderings are equally likely, but we want the red point to be in the K plus 1 position, and that allows us additional n factorial on the numerator. So it's n factorial over n plus 1 factorial, which is 1 over n plus 1. Do you see that it simplifies? When it simplifies, you right away suspect that there is, in some sense, a simpler argument. And the simplest argument is it's completely indifferent from the perspective of position, right? So the K plus 1 position, it's like the secretary, like, I don't care, I'm just doing my job. I'm just sitting here until 5 o'clock and I'm out of here, right? I don't care if it is a black point, a red point, I don't care, right? So there are n plus 1 possibilities for the K plus 1 position, and they're equally likely, right? So the probability that it's the red point occupying that position is 1 over n plus 1. So that's the other way of thinking of it. You can either think of all of them together, or right away you can see it's 1 over n plus 1. So you see how beautiful it is. This integral, if you do not have a computer, it's pretty painful to solve for an arbitrary K. But here, without any computer, you right away know the answer is 1 over n plus 1. So this thing is equal to 1 over n plus 1. Cool. And this is what it tells us. It now tells us how to figure out beta of AB for any integer a and b. So here is the situation, right? If I have x to the a minus 1, b to the minus 1, so altogether it's a plus b minus 2. If I add this plus that, right? Altogether it's that. It choose a minus 1. That's very similar to this formula, exactly the same, right? What is that going to equal to? That will just equal to 1 over this number plus 1. So it's 1 over a plus b minus 1. And all you have to now do is, this is your beta. This is your beta AB, right? So what you have to do is you just have to divide it. I mean, sorry, that's not the beta AB. I'm sorry. I just take this number and divide by that number, and that's what you get. That's your beta AB. You see, beta AB is the integral without the corrective factor. That's pretty much what the beta distribution is. This is just scary, but this is the beta distribution, just the x to the a minus 1, 1 minus x to the b minus 1, right? That's the beta distribution. And this is the corrective factor, just integrated from 0 to 1, and that's what you would get. So you need to take this number and divide it by this number to get the integral to equal to 1, right? So that's what it tells us, you see? It tells us how to compute beta of AB if a and b happen to be integers. Good. So here we now are going to try to understand how to update probability based on evidence. Okay, and just to make it slightly a concrete example, we would say we have a coin and we don't know anything about that coin. It comes up with heads with probability p. Right? I didn't toss it. I just know that it will be heads with some probability p. Maybe it's a two-headed coin, so it will be always p. Maybe it is never equals to heads. Maybe it's a fair coin. We don't know. So we have just this distribution p, and the unbiased assumption, of course, will be to initially believe that the coin could be equal to anything. Okay, it is equally likely to be any probability of coming up heads. But you don't have to make that assumption. You can make a more general assumption. Even more generally, it's fair to assume that it's some beta distribution, some initial beta distribution. Why? Because the beta distribution already includes the assumption that it's equally likely. You understand? So you're making even a more general assumption. It's up to you. The point is, if you know it's a beta distribution, you will see that the updated distribution after the evidence will always happen to be a beta. So it's after you introduce more evidence, it just happens to be a different beta distribution than the one you predicted. You will see that in a moment. But for now, you see, natural assumption and biased assumption, I have no idea, right? Just like when you meet a person, it's a blank slate for you. You do not know what the person is. You haven't interacted with the person. You don't know anything. Then based on some evidence, you will have an updated distribution based on something that you know about the person. You know, maybe this person is very funny. All right. And then you have, or you know, right? So you just update your information later on. So here is how we go about it. So it involves a lot of letters P. So I decided to call the random variable. I called it W for the German word for probability, Wahrscheinlichkeit, and we're assuming that the W equals P with which it has distribution. It has a density function which is some beta AB. Right, some beta distribution at AB. Everybody at least has a sense why we assumed it might be a beta distribution. That's because it allows us quite a lot of flexibility, and it already includes the assumption that it's equally likely to be any value p. Right? So, and then we have x. X is the number of successes that we will have, right? So I want to know how to update this probability after I witness the number of successes, right? So I'm going to toss this coin n times, right? independent time. Each trial is independent, and I will observe how many outcomes there are where it comes up heads, and based on that, I will update my initial assumption, which would actually begin with, of course, I would not have any bias. I would begin with a horizontal line, with the uniform, right? But let's say I already have some knowledge about the coin, so it's some general beta distribution, and I will see how my knowledge is to be updated. So we need to calculate the marginal density function. So what's the marginal density function? We will talk a little bit maybe more about margins, why it's called margins, but the idea is it's just the conditional, right? So what's the density conditional on the fact that I had k successes, right? So this is the original function. I need to update it, conditional on k successes. What is that? And I give it the name g, just so that I don't have to write this. Yeah. So what do we need to know about it? Well, first of all, a good thing to know is what is the probability that W is between P and P plus dP, given that X is equal to K. That's given that we have those successes. That's going to be this function multiplied by dP, the density function multiplied by the width. That's how it's supposed to be, right? So this probability is this expression, and we will try to see what this expression is equal to in terms of the original F. Make sense? So what is GPDP? Well, it's this probability, and I can just readjust conditioning, right? I can just recondition. So that's the same as saying probability that X is equal to K, given the second part, times the probability of this first part, divided by the probability that X is equal to K. Good? Now, what do we get there? So what's the probability that X is equal to K? Well, probability X is equal to K is this integral. Same argument, it's just not easy to solve this integral. Remember, same argument with the dotted points, with the black points and the red one, except now f of x here might not equal to 1. So that's the integral. That's for the denominator. Now, of course, probability that X is equal to K, given this information, that's just going to be a binomial. Right? Because what is this? This means that W is equal to, essentially this means to me that W is equal to P. It's P plus something small. So I view it as if the probability of success is exactly P. So what's the probability of having K independent successes? That's this. Good? That's K independent successes. So I hope you understand this line. Just to think about it, this is this line, and then I just have this line, and then of course, what is this line? W is between P and P plus dP. That's approximately the original function F times dP, right? So that's F times dP. So we get this expression. So GP dP is this expression. Looks very complicated, but it's far less complicated than it appears. So what you should note is, okay, this is just a number. The denominator is just some number. I can ignore it for a moment, right? It's just a bunch of numbers. And what's true about those numbers is that if I integrate this function g from 0 to 1, I should get 1. So all those numbers, when I factor them, they're just reciprocal of a particular integral. So what is that particular integral? So if we look at f of p and at this expression, what is f of p? F of p is p to the a minus 1, 1 minus p to the b minus 1 times some constant, right? So there is this constant, there's a constant here, and this is just a constant. Yes. So what do we get? We get essentially that all the variables, they add up to what? They add up to p to the a plus k minus 1, 1 minus p, b plus n minus k minus 1. That's the variables. You see, are you with me, guys? You might be confused. Should I write it? Should I write it in better detail? Yes. Let me write it possibly on the whiteboard. So maybe that would help. All right. Let's see that. Here is where we began. We have G, P, D, P. Right? And that's supposed to represent the probability that W is in the interval of P to P plus dP, given that the number of successes equals to K, that's the marginal density. That's clear so far, right? So because we have this evidence, we play this experiment and we want to know what's the new probability given that I have this extra evidence, that I flip the coin K times now and I have this information. Good. So what do we have? Then we just rearrange it. We rearrange it and we say this is the same as probability that X equal to K. Given that W is in the interval P plus dP. Right? Times what? Times the probability that W is in that interval. Divided by probability that X is K. So far good? You can use anything you like. Those are just symbols, right? So just if you don't get confused, maybe you don't like the P used here, but it's all the same. Yes. Okay, so what do you do here, guys? So let's say P equals to K. I can expand it, but it's just a number. Do you agree? So this thing, it's just a number. Okay, just a number. It doesn't, you see, if I evaluate it, it would not depend on the expression P. You see, it's P is a function. You say P is varying from 0 to 1 in this situation, right? P is a variable. It's not really, it's not a fixed number. Good. Now, what is this? What's the numerator? The numerator, this numerator is equal to n choose K. And here I make the approximation. If W is between P and P plus dP, that means essentially the probability is kind of P, right? So this is saying what's the probability of flipping the coin n times and getting K successes given that the coin lands heads with probability P. So what is that? This is n choose K, P to the K, 1 minus P to the n minus K. Agreed? Keep in mind that what's in red is just a number. Good. And then what is this? W is in between P and P plus dP. That means we have the original function. That's the function Fp dP. Yes, divided by what is in this red is just a number. I'm not really interested in this number because you will see in the expression that I can figure out all the numbers together and I will know what they are. Good. So what is Fp dP? Again, I would like to draw your attention to this fact that, okay, so this is also just a number. No idea what. Of what f of p dp? No, by assumption, f of p was what? F of p was the beta distribution, the prior distribution, right? So So in other words, you see, you approach life with some prior experience. In other words, when you are born, everything is supposedly right. I mean, maybe you're in pre-born with somebody, but imagine you're training a machine or something, right? And initially, it's equally likely to assume that, let's say, any word means anything, or any sentence. You see, you have different interpretations of a sentence or a search, and you might imagine everything means the same. And then once you train the machine, the machine already has a bias. It knows that it's a when you type Mathematica, it's most likely you're not searching for Principia Mathematica by Newton. It's more likely you're searching for the software Mathematica by Wolfram, for instance, right? So it's that type of thing, right? But then if you type many times Mathematica and you don't click and you're saying, well, Newton, then the machine can learn, okay, actually you're searching for Newton's Principia Mathematica. You see, so you update the probability based on new evidence, so to speak. That's how it's supposed to work. We're trying to learn how the update is working. So initially, f of p will just be equal to 1, right? But perhaps you already have prior bias, and initially we presume f of p equals to some beta distribution, right, with parameters a and b. And we make this more general assumption. Make sense? So what do we get here? We get, again, I'm going to write this as, look at it, this is just a number. Then what do we have here? Here we have p to the k, 1 minus p to the n minus k. And then I expand f of b. F of b is 1 divided by beta ab. 1 divided by beta AB of p to the a minus 1 minus p to the b minus 1 divided by number. Again, what is this? It's also a number. You see what I'm doing? I mean, it has a lot of things that might be confusing or scary, but I think, oh, they're just numbers, right? What matters here is that I can combine this expression and this expression. I can combine them into one expression, yes? Namely, if I combine them into one expression, what do I get? I have the expression is p to the power of a plus k minus 1. You agree? Times 1 minus p to the power of n, so b plus n minus k minus 1. Yes? So you see what I mean? So I have, you see, when you see this expression here. This is what in essence, so we have those numbers, they can be simplified. Number times number divided by number. So in essence, we see that we get, when we simplify, we get number, right? Number multiplied by p to the power of a plus k minus 1. 1 minus p to the power of b plus n minus k plus 1. Yes, and this is what determines what the distribution is, okay? Because we calculate, there is of course the dp part, but the dp part is now a vestige. We can divide by it. We have gp, so gp times dp is equal to this. So all we now do is just cross out dp. And we have what is gp essentially. Gp is this function multiplied by the number. Now gp is a density function. Do you agree? If it's a density function, it must integrate to 1. And the only way it integrates to 1 is that if this number here, what you're seeing here, is 1 over, so that means that when you simplify it, it means that this thing, it has to be 1 over beta of A plus K, and then B plus N minus K. That's the only thing it can be, because that's what the beta is doing. It's just a corrective factor. You understand? I don't need to solve it. I don't need to just, if I did everything correctly, I know this has to be still a density function. It still has to represent probabilities. So when I simplify what n choose k and every other number I get all together, that must simplify to a beta. So what the entire discussion is supposed to tell us? So the entire discussion is supposed to convince us of this fact that when you start with a beta distribution, you stay in a beta distribution with updated evidence. This is what we just arrived at. Okay. Understood? So for instance, here is how we might apply it with one example. A coin is tossed 1,000 times. 550 tosses come up heads. Estimate the probability that the coin lands heads. Okay, so in other words, estimate the probability P that that when you toss a coin, that I'm sorry if my question is weirdly phrased, maybe a little incomplete. What I mean is this: you have this evidence, right? Now I'm holding that coin and I'm going to throw it. Predict the probability that the coin will land heads. Okay, what do you think is the probability? Make sense? You have this evidence. I didn't tell you the coin is fair. Do you agree? I never said a fair coin. I said the coin is tossed. And we are assuming two things. Very important. We're assuming that each of the tosses was independent. There was no bias here. And we see that in 1,000 tosses, 550 are heads. I do not know. I mean, do I know if it's fair or not? Let me try to understand it, right? So here is how I begin. So my initial assumption before I have this evidence is that, okay, it's beta 1,1. In other words, I assume it's uniform. I do not know who you are. I don't know if you're going to give me a loaded coin or a fair coin or what you're going to do, right? I don't care. It also doesn't matter if I'm too naive or not. It doesn't matter. I will update based on the evidence. Now, the evidence is this. The evidence is that there were 550 successes out of 1,000 in total, right? So that means the update is what? The update is, remember, here is the update. What do I do? To the first parameter, I add the number of successes. To the second parameter, I add the number of failures. So this is the number of successes. This is the number of failures. So successes were 550, failures were 450. So I have beta 551 and 451. That's my new beta. I began with this beta, with completely naive beta, and now I have this beta based on the evidence. Yes. And now let us look at the possible. Yeah. So let's see what this distribution looks like. So A, number of successes plus 1 is 551. Number of failures plus 1 is 451, correct? And then, okay, so let's see this distribution. Yes, here it is. You see it? So we can see there is a small blip. Whoop. It's very unlikely, as you can see by the graph, that the probability is 0.2 or 0.4 or any number close to 1. It's very likely that it's somewhere between 0.5 and 0.6, right? So for instance, let's consider what we have here. Let's consider what's the probability that, and what did I do in my question? Let's do it the same way. So here, let's say, right? So I want to know, so what's the probability that, so let's consider what's the probability that the coin is between 0.51 and 0.59, right? What's the probability that it's actually between 0.51 and 0.59? So in other words, what's the probability that the probability for this actual coin is between this number and that number? You see, it's always an estimate. I cannot, based on no matter how much evidence, I cannot predict for certain what's the exact probability of the coin, but I can approximate it. With more evidence, I can kind of zoom in on it, right? So what do we have here? So let's say, what's the probability that the coin is between here we can say let's say between 0.51. Okay, so you can see the probability that, what was it, 0.51. This is the probability. The probability is 99. So you see, it's more than 99% likely that the coin will land on heads more frequently than 51%, right? You see what I'm saying, right? And you have some, yes, what options do they have here? What about, let's say, you can see, let's say 0.6, right? 0.6 based on the graph is interesting. And let's say, what's the probability? It's less than that, right? You can see 99, well, very, very likely less than 0.6, right? Tremendously likely less than 0.6, tremendously likely that it's bigger than 0.5. You see? So it's between 0.5 and 0.6 with tremendous likelihood. And you can kind of, you know, this is you're very, very confident. It's between 0.5 and 0.6. You see what I mean, right? So you don't, if you have more evidence, you can be even more confident, maybe for, you know, within fewer digits. That's the idea. Make sense? So in my notes, I kind of I kind of drew it. You can see I decided to say here is 0.51 and here is bigger, and I estimated some sort of some probability here. So it's extremely likely to be in this region. So here is another example. In a city of 12 million inhabitants, it is wished to estimate the number of people that contracted a certain disease. As you remember, it's also when I was writing, it was really remarkable how everybody test everyone, test everything, right? When you do that, when you test every single person without stop, what do? You confound the data. You make it impossible to understand anything. It's like you muddle the water, you know, you just make it as confusing as possible and as stupid as possible, of course. That's more or less New York's population, right? And let's say what is known, 100 subjects are randomly selected to be carefully tested. You see, so let's do that, right? Let's instead just look at the population and select. We want to understand how spread is the disease in the population, right? So what we do is we select 100 individuals and test them carefully, not some silly exam, not some silly test, not some quick test, not just test them carefully. If, of course, it's not always easy to select 100 people, but if you go to Australia, you can now do that by force, you know, so it's not a problem anymore. And so what do? You begin testing them, and you find out that 2 are infected, 2 have the disease out of 100, right? What should you conclude about the spread of the disease for the general population? Okay, so initially, again, you assume the spread is between 0 and 100%. You have no idea. It's either I'm having a stroke or my computer is burning, so that's why I'm thinking, okay. It smells of something fried. It bothers me. So yeah, so P is beta 11, and the results of the update is what? What do we know, right? So we have tested 100 individuals. So how do we update? We have performed the experiment 100 times independently. 2 successes, 98 failures. So now we have a beta distribution of 3 and 99. Yes. So this is our distribution. Let's try to write it in the software so we can see how the distribution now appears. So A, I said, was 3, I think, and what was B? Forgot. B was 99, correct. Okay, and B is 99. Do you see now? This is the hill, and you can see where it goes down, right? You can see that essentially we are expecting at the very most, I mean, what does it look like? At the very most, let's say, what's the probability we have more than 0.1, right? A very low probability that it's more than 10% of the population. You see? So we have an estimate now that it's between, and that's only out of 100 individuals. You understand? The more individuals you pick, the more accurate it becomes. So for instance, if we have, let's say, 30 individuals, 31 out of 1,000, and then you have what's the and so let's say 30, and here we have, let's say, 971, right? So you can see it drops to what? Let's say, so let's say now what's the probability? Let's say you can see what's the probability? 0.01. 0, I mean, it's bigger than that. Let's say it's almost 0.05. What is that? You see, it's very unlikely that more than 5% are sick, for instance, right? If you have just 1,000 individuals tested and this information, you get very accurate results, you see? And 1,000 compared to millions of individuals bothered all the time, you see, it's much, much more convenient, you understand? Right? Pretty interesting distribution. And here is one more question. So, a new medicine against migraine is going through trials, and participants are admitted to the study. So initially, what is the probability that X, the number of participants whom the medicine helps, is equal to K? So I want to predict what's the likelihood initially that K people will be helped by the vaccine, by the, I mean, migraine. By the vaccine, I mean, it will be a different story, right? Not let me going there. So yeah, so what do we have? Probability that X is equal to K is by default, we take the, without knowing anything about this medicine, we take the default beta 1,1, the uniform. That's the uniform random variable, right? And that's just this integral. And we already solved that this integral is equal to 1 over n plus 1. We know that, right? So the probability that it will help any number is the same, you see, because we know nothing about it. So we say, well, it doesn't, it's just as likely to help one person as it is to help 0, as it is to help all, because we have no bias, we have no idea. This is just meaning just guess, absolute guessing, right? So that goes, why is n plus 1? Because it either helps 0 or 1 or 2 or 3, you know, and we're just guessing. Makes sense, right? Each quantity is equally likely. That's what we're saying. So it's pretty convenient, isn't it? And so what next? Now, given that that all the participants in the study are positively affected, what's the probability that the true potency P of the drug is greater than 1/2? Okay, so it helped. Let's say we had n participants and everybody experienced a positive result. What's the probability that the actual potency is bigger than 1/2? So now we have n successes and 0 failures. So it's now updated to be n plus 1, 1. Yes? And what is that? That means that we have 1 minus p is to the power of 0 and p is to the power of n, right? And we know that this integral, it's an easy integral. This integral actually happens to also be 1 over n plus 1. Is this integral? Right? And so beta of n1 is actually also equal to 1 over n plus 1. This is the probability that x equals to k, but the beta n1 is equal to 1 over n plus 1. Good. And so the probability that the probability of the drug is bigger than 1/2 is 1 over beta, which is n plus 1 multiplied by the integral from 1/2 to 1 of p to the n dp, and that is 1 minus 1/2 to the n plus 1. You can see this number, if n is very, very large, then you are very convinced that that this probability is almost 1. Almost certainly it's better than 1/2, right? It probably, even if you select a much bigger number, right? If it helps everyone, you know, eventually this number is so small that you're getting very convinced that it's a very good medicine. Good. How is my exam coming along? Yes, is it good, enjoyable? Slowly but surely, like alive to its end. So relax about, again, guys, right? Do your best. Don't be panicked. I don't want you to be panicked. Do panic, of course, if you decide to cheat and I decide to get upset about it, then you can panic. But if you, I tend to, I tell you, right? I had people receive grades from you after they died, post-mortem. It happened, right? Somebody dies and the family wants the grade, and here it is. It's B plus at least, you know. So you don't need to. Good. So relax. It's the only reason I give those problems like this is hopefully because I want you to understand the material, hopefully, right, for your enjoyment, that you actually get obsessed about it and be very interested and learn something from this class. That's all. But I don't really want to harm you too badly, unless you cheat. Then I might get upset, which I'm sure you will. But you know, what can I do? I do my best to warn you against, but my beta distribution is extremely biased in the assumption that you are cheating, and which is I witness it all the time. All right. Now we are going to talk about exponential random variables, which is also rather interesting. And they actually relate to Poisson distribution, but we might not get to that relationship in this class. Yeah, don't search for meaning from Google, right? They sell it. So here is the definition of an exponential distribution. It is f of x equal to lambda e to the minus lambda x for x is bigger than 0. Okay, and of course the cumulative distribution is what? It's 1 minus e to the minus lambda x. This is easy to integrate, right? Integrate it, it's just e to the minus lambda x with a negative, and so when you take the integral from 0 to infinity, that's you would get 1, and if you take the integral from well, I mean, let me not say more. You understand how to calculate this. It's not hard, correct? Not hard. So also you might as well look at exponential distributions where lambda is equal to 1, because all others can be surmised from them, right? Just like with standard normal distribution, same thing we can do for other variables. So for instance, suppose that x is exponentially distributed with parameter lambda equal to 1. Then if I want to take y equal to x divided by lambda, y is x over lambda, then the probability that y is less than or equal to lambda is the same as x over lambda less than or equal to y, which is probability x is less than lambda y, which is the integral from 0 to lambda y of e to the minus x, which after integration gives you this expression. And if you differentiate, you get the distribution with the lambda. There is a y missing here, but you understand, right? It's lambda e to the minus lambda y. Good. So by taking the exponential with parameter 1 and dividing by lambda, I get exponential with parameter lambda. Similarly, if I begin with an exponential with parameter lambda, I can go the other direction. What I do is I just take x equal to lambda y, and you will see that this x will be exponentially distributed with parameter equal to 1. Just carry out the calculation. You just figure out, of course, why do you divide, why do you multiply this? You can just figure out why. Think about it. Okay. It's just always interesting, of course, to come up with such calculations on your own. All right, so now let's talk about the expected value and variance. So the expected value of x is this integral, which you do by integration by parts, and you arrive at the number 1. You sit, carry this calculation, you get that the answer is 1. Similarly, if I take the expected value of x squared, I carry out integration by parts until I get the number 2. There is a faster way of doing that. Maybe if we have time, I will teach you about moment generating functions, even though my notes are not prepared for it. Good. But this is what you can do. This is expected value x, expected value of x squared. And so variance is what? Variance is equal to 1. It's a matter of just integration by parts, nothing more here. Good. So that means that in general, if y is distributed with parameter lambda, then the expected value of y is going to be 1 over lambda. And the expected value of y squared is 2 times 1 over lambda squared, just an easy modification. Because once I know the expected value of x, I just multiply by 1 over lambda to get the expected value of y, and by 1 over lambda squared to get the expected value of y squared. And so when you simplify for variance, it's expected value y squared minus the expected value y squared. You get 1 over lambda squared. Just a lot of calculations. But what's interesting about this distribution? So this distribution is supposed to model, let's say, possibly, it's actually a very strange distribution. I'll try to convey how strange, but it might model the amount of time that elapses until an event occurs. Okay. So how long do you wait until something happens? So here is an example. So first, and it has also a curious type of thing. It means you ask yourself, what is it good at modeling? Is it good at modeling, like how long do you wait until your, I don't know, until you get sick, or how long do you wait until you have a very fortunate day or something like that, right? So those might be somehow distributed. And how long do you wait until your device breaks down? That's actually in some sense a bad analogy to it, because you will see here. Okay, here is maybe a better example. So suppose the time it takes me to grade one of your tests is exponentially distributed with mean 1 month. Okay, given that you've waited for the results 1 month already, what is the probability that it will take another month or longer for you to get back your tests? Okay, that's maybe a good example of waiting for an event. Okay, so if it's exponentially distributed with one parameter 1 month, this is the question: what's the probability you wait longer than 2 months, given that you waited already longer than 1 month? Yes, and that's the same as the probability that you wait more than 2 months and you wait more than 1 month divided by the probability you wait more than 1 month. So the numerator is just the probability that you wait more than 2 months divided by the probability that you wait more than 1 month. Yes, this is not necessary in this calculation. What is this probability, guys? It's the integral from 2 to infinity of e to the minus x. Just you don't need this whatever I wrote here. It just it's enough to write integral from 2 to infinity, not from 0 to 2. from 2 to infinity. And on the denominator, it's the integral from 1 to infinity. So the integral from 2 to infinity of minus x is going to be e to the minus 2. The integral from 1 to infinity is e to the minus 1. Are you with me, guys? I'm speaking over it, but I hope you understand how to carry integrals. This is, by the way, in my opinion, I would have erased it. Now it's much easier calculation, just like this, right? The integral from 2 to infinity e to the minus x dx is what? It's minus e to the minus x evaluated from 2 to infinity. Plug in infinity, it's 0. So it's e to the minus 2. You agree? Yeah. No problem, yes? So what do you get? E to the minus 2 divided by e to the minus 1 is equal to e to the minus 1, which is the probability that t is bigger than or equal to 1. So what is it saying? It is saying that the fact that you waited is not going to affect how long you have to wait any longer. Do you understand? So there is no memory. If you waited for the exam 1,000,000 years, the probability that you will wait for the exam another 1,000,000 years remains the same. If exponential distribution modeled the life of a person, then the probability that you will live another 100 years will be, if you're 99 today, right, will be the same as if you were just born. You understand? So it's as if whatever happened doesn't matter. It's all behind you, but it's not affecting. It doesn't mean the probability is high or low, but the fact that you already accomplished something will not affect your probability of having to of surviving longer. Okay, that's very weird. You wonder what can such a distribution model, right? It doesn't seem that that let's say devices that are old are more likely to break. It seems that if your computer worked without restarting for 7 years, you would not expect the probability to be the same as if you just opened it from the box. But that's what the memoryless property is telling you, right? So this is the definition of memoryless property. A continuous distribution is said to have memoryless property if the random variable satisfies this condition: the probability that x is bigger than or equal to s plus t, given that x is bigger than s, is the same as the probability that x is bigger than t. You understand? So in other words, the probability, this is saying what? The probability of waiting t, given that you already waited s, is the same as if you never had, you just started waiting. You just nothing have occurred. You see? Does it make sense? Here it is. Here is the calculation that we verify that the memoryless property holds for the exponential random variable. So take any exponential random variable with parameter lambda. And I want to calculate the probability that x is bigger than or equal to s plus t. That basically that some event happens in more than s plus t time, given that you already waited for it s units of time to happen. Right, so this is just this ratio. It's the integral from s plus t to infinity divided by the integral from s to infinity. Yes, and when you simplify it, what do you get? You simplify this, you simplify that, you get e to the minus lambda s plus t divided by e to the minus lambda s. You just get e to the minus lambda t. So it's the same as if the s amount of time that you waited doesn't count. Now that it passed, it does not affect the likelihood of this event to occur, right? So that's what you should keep in mind when I grade your exams as well, right? Just because you waited for 3 weeks, you might it's as if you just gave me the exam today. It doesn't mean anything. And there is, of course, this theorem that tells you that if you have a continuous random variable, only the exponential random variable can have the memoryless property. It's the only variable that has this property in the continuous case. Why? Well, let's look. That's the theorem. So if x is a positive continuous random variable that has the memoryless property, then it's exponentially distributed. So let f be the cumulative distribution function of x. And then this is called survival rate function. You see, so that means that the probability of overcoming the time frame x, right? So it's like, you know, for our lifespan, let's say f of 99 is almost 100%, because very few people live beyond 99 years, right? But 1 minus f of 99 is the probability of surviving past 99 years. That's how you should think of it, right? So that's known as the survival, I think it's known as the survival rate function or something like that. I tend to forget. But it is probability that x is bigger than x. And we have the memoryless property. By the memoryless property, what do we get? We get that probability that x is bigger than s plus t divided by probability x is bigger than s is equal to the probability x bigger than t. Do you agree? If we assume that this random variable has that property that doesn't matter how long you had to wait, this is what it means, correct? And if you translate it to the survival rate function, it means the survival at s plus t divided by the survival at s is equal to the survival at t, which means the survival of s plus t is the survival of s times the survival of t. You see, this, the addition to multiplication looks like the exponential function. Correct? And let's try to understand what happens at an integer. So if I pick the integer n, it's n minus 1 plus 1. So I can write it as g of n minus 1 times g1. And I can break this one again into gn minus 2 and g1. And in essence, I can break it into g1 times g1 times g1. I have g1 to the nth power. You see, it looks like it's behaving like an exponential. And that means if I do that for, let's say, I want to know what's g of 1 can be written as 1 over n plus 1 over n plus 1 over n. And I break it apart, it's g of 1 over n to the n. Right? Which means that g of 1 over n, I just take the 1nth root, it's this. You see, g1 over n is g1 to the power of 1 over n. That quickly allows me to calculate at fractions. What is g of m divided by n? That's simply what? That's simply g of 1 over n plus 1 over n plus 1 over n m times. So it's g1 over n to the m time, which is then g of 1 to the 1 over n to the nth power, which is g1 to the m over n. I say a lot of m over n and g. I hope you are still following me, right? I mean, I imagine it's very confusing and unpleasant to hear g, m, n, you know. If g, then m, then n, then n and m, you know. So I'm sorry for that, but I hope you look at it and even without my words, you follow what's happening, yes? So you see what we have verified. We see that g at any rational number is g of 1 to the power of the rational number. And if you studied analysis, you know that continuous functions are completely determined by what they do to rational numbers, because rational numbers are dense in the number line. That's a very useful property. So what that tells us is that g of x is g of 1 to the power of x, which allows us to know that it's exponential, and I can write g of x as e to the power of ln of g1x, which I can write like this, which I can write as e to the minus ln of 1 over g1 times x. You can see that this is now my parameter lambda. I can set this parameter as lambda, and we have g of x is e to the minus lambda x as desired. That's my, and if I take the derivative of this function, or of this function, I take the derivative, I get this density function. So you can see that it's true. I did not lie to you. Yes. And again, as I want to emphasize, it's tremendously difficult to comprehend what could this distribution model, right? As Alexander Gradinsky says, I mean, what could be memoryless, right? Alexander Gradinsky sang, "Nothing on earth passes without a trace, and bygone youth is nonetheless immortal," right? And so you understand with what feeling this is being sung. I'll play a small excerpt from this song, and if you decide you want to listen at the end of class to the full thing, be my guest. Yes, you see how some people are passionate about the exponential random variable. Yes, very good song, guys. If you want to listen to it fully, it's a very good way to end the class. So, indeed, what on earth is memoryless? What on earth is not leaving a trace? Well, you can say, first of all, some physical phenomena such as radioactive decay truly exhibit memoryless properties. So if you take it seems, so they say, right? Take an atom that's about to release an alpha particle, right? If it might have not released it for a very long time, and suddenly release it, you see? And the fact that this atom did not, this atom released the particle just a second ago, and this one did not release it a million years, they are now the next moment equally likely to release the next one. Do you understand? That's kind of, so apparently in this phenomenon that is done so. Then of course the exponential distribution is connected to other distributions. So there is it's really connected to the Poisson random variable, which we already all know and dearly love, right? So, and it's a very interesting relationship, the Poisson paradigm. Very truly interesting relationship. And of course, you can build other distributions. So it's like a building block, a small part in distributions that such as that are more flexible, the Weibull distribution and other distributions of the sort. You see, so it's a distribution that you learn to begin developing deeper intuition for things, right? And then of course this reminds me of a person that that I've known named Dave, right? And when I think of the exponential distribution, I of course always think of this guy, as he never came anywhere on time whenever he was scheduled, and I even had Dave correction time. In other words, you know, he would say, let's meet at 5, and I would right away add 45 minutes before I even bother exiting, you know, the house. So I implemented this algorithm, Dave correction time, which of course he realized I'm implementing this algorithm and came even later, so that I will have to wait longer. But that, I think we will talk about the next class. Yes, well, I guess then Dave is famous, I suppose. Yes, he would definitely have to make me wait. And there were cases where I had to wait for over an hour. Yes, that's the type of person he was. Yes. So I'll stop the recording, guys, and if you and play the song. And if you have questions, you will let me know.